Okay, welcome everyone. Welcome to this webinar. My name is Iqbal Singh Josan, and I'm going to present this webinar today on wireless receiver engineering. You can interact with me with typing your questions at the bottom left of your screen in the chat box, and that's how you can interact with me. Okay, let's move on to the outline of this webinar. So today we are going to learn about the different receiver characteristics that any wireless receiver, how do we define, how do we characterize it? Like it could be sensitivity, noise, selectivity, stability, spurious responses, phase noise, dynamic range, or automatic gain control. Now, after understanding all these characteristics, we'll move on to the various receiver topologies that are in use. We will we'll learn about the super heterodyne receivers and the direct conversion receivers and what role they play in the conventional receiver architectures. And then we'll touch base on the modulation techniques, specifically the digital modulation techniques, which are mostly in use in the cellular communication networks. So we'll understand quadrature amplitude modulation, spectrum, and the different characteristics, and also learn about the OFDM, the orthogonal frequency division multiplexing. And finally, we'll introduce ourselves to the software-defined radio, which is an emerging receiver architecture in wireless communications. Okay, so with that in place, let's restart. Now, this is a very basic picture of a wireless communication system where you have a transmitter at one end and a receiver at the other end, and you have a channel, wireless communication channel in between. Well, to be more specific and more practical, this is the actual system that you encounter in the field, where on one end you have either a BTS or a node B or a E node B, depending on what type of technology is being used. It's a GSM or a UMTS or a LTE network. You will have a transceiver actually. Transceiver means you have both a transmitter and a receiver at either end. So similarly at the UE or the user equipment, which is the handset or the cell phone, you also have a transmitter and receiver combination. And so you have two links actually. There is an uplink and a downlink. So downlink is when your base station is transmitting and you are receiving, the handset is receiving. And the uplink is when your handset is transmitting and the base station is receiving. So both these links are important, and we have to look at both of them. Okay, so this we just listed all the different characteristics that we can apply to any wireless receiver, whether the receiver is on the base station or the receiver is on the handset. Well, sensitivity. So what does sensitivity mean? So it simply means that you must be able to detect very weak radio signals. So if we recall from our previous webinars on link budget analysis, we remember that because of the RF propagation losses, the signal really becomes very weak at certain distance. And we have to really know that what should be the strength of the signal for our receiver. So both for downlink and uplink, it matters. A few examples here how sensitivity of a receiver will be mentioned in the literature or in the specifications of that particular equipment. So for example, for a node B, you could say it's minus 121 dBm, and for a mobile or a handset, it's minus 117 dBm at a bit error rate of 10 exponent minus 3. So usually the bit error rate is also mentioned that to be sure, like at this signal level, this is the error rate you will encounter when you're transmitting any signal or any data. Another example that instead of dBm, you could mention the sensitivity in terms of microvolts also. That microvolts, 1 microvolt is the level of signal that this is the weakest signal I can detect for a 10 dB signal to noise ratio with this much bandwidth, 3 kilohertz bandwidth. So it's always mentioned in conjunction with some other parameters which are relevant for the receiver. Now, sensitivity. Now let's revisit the downlink budget for LTE. This is a slide from the previous webinar. So here, you know, if you recall the receiver sensitivity at the bottom of the black line, here we came out with minus 88. That is the receiver sensitivity we need for the user equipment. And the link margin, we came out with 18 dB here. Now, for uplink budget, you know, the uplink means the E node B sensitivity. Here is minus 109. So you see the E node B can detect even weaker signals. Why is that important? Because, you know, handset has a limited computing power or limited electronics that can be built into it in a handset. So there is a limit to how much sensitivity you can achieve on a handset. Although, you know, with With every year, you get more and more sensitive handsets, but still there's a limit. On E node B, the limit is a little more relaxed actually. You can put more stuff, more bang in the box, in the E node B box. So, and it's required also for E node B, it must be more sensitive handset, because handset transmitter will not be as powerful as the E node B transmitter. So the signal will be even weaker when it arrives at the E node B. So that is why we are coming out with even better sensitivity at the E node B compared to the handset. So this is just a reference from the previous link weight analysis and how the sensitivity plays into here. Now next is the noise. We have seen this before. Yeah, so receivers are susceptible to noise. The noise could come from various sources. It could come from the atmosphere. It could come from the earth, which we take a reference temperature for earth to be 290 degrees Kelvin. It could be coming from sun, from galactic sources, from cosmic background. There could be man-made sources of noise too, the EMI, electromagnetic interference. And the antenna could generate its own noise too, right? Noise could come from the feeder line, the feeder losses, and the noise generated inside the receiver. So all these sources of noise must be considered, and we should be able to, if we know what's the noise power at the receiver, we can characterize the receiver, that this receiver generates this much of noise, or this receiver is detecting this much of noise from the environment. So we'll quickly go through these slides. The noise power is given by this very basic formula. The Boltzmann's constant comes into play here. We have the equivalent receiver noise temperature and the noise bandwidth. In terms of dB, for our calculations, we have used this formula with an example here, which for minus 144 dB, W at equivalent noise temperature of 290 K and a bandwidth of 1 megahertz. The same criteria we can apply to any receiver for any bandwidth. So here is an illustration which shows a reference for various sources of noise and various noise temperatures that we can consider. Like for natural noise, for the sky, we consider a temperature of 30 degree K, and for earth, we consider a temperature of 290 degree K. For antenna, this is a very general antenna, 290 degree K. For feeder loss is 75 degree K, and for receiver temperature is very high here, because inside the wireless receiver there is hardware, this electronics that generates heat, and that heat causes to generate a lot of noise here. Okay, noise factor. It gives us a measure of how much noise is added by any active device, any amplifier, any RF amplifier or a power amplifier inside a receiver. So you see these three different expressions. For the noise factor is simply a ratio of the signal to noise at the input to the signal to noise at the output. In terms of dB, we have a different terminology. It's called noise figure, which is 10 log of noise factor. So I'm quickly going through these slides because I've seen this before, those of you who are attending from previous webinar, but they are very good reference. The noise does matter for any receiver. For cascaded sources, we have the Fry's formula, and one thing to note here is that it's the front end amplifier which is the most important here, whose noise factor figures into the total calculation. So that's why we must have for very weak, we must have a low noise amplifier at the front end. Now, before we move on, let's pause for a while and try to answer this question. So which one is correct here? Mobile handsets generally have better sensitivity than base stations. Human body thermal radiation must be factored in handset noise temperature calculations, and noise factor is 10 times log of noise factor. Higher gain of only front end RF amplifier proves the noise figure of the whole receiver. So please type in the right answer here. So number one is not correct, because as we just discussed, the mobile handsets are not as sensitive as the base stations. They need not be actually, So human body thermal radiation, we don't need to figure this out, because we already are taking the environment, which is 290 degree K from the earth. So noise figure 10 times log of noise factor, well, that is true. So higher gain of only front end RF amplifier improves the noise figure of the whole system. That this is correct. Number 4 is also correct. So number 4 is also correct here. If we recall the Fry's equation, when we have a cascade of amplifiers, so it's the front end that matters the most actually for noise figure. Well, move on to selectivity. So what is selectivity? Selectivity means that we must be able to select the desired signal that we want and reject all the others. Now, in a typical scenario, you have a smartphone. We have all types of frequencies around us. We could have in this typical illustration, we could have a 3G UMTS at 1960 megahertz coming from a node B, or we could have a LTE 740 megahertz coming from a node B. We could also have a Wi-Fi 2.4 gigahertz and a GSM2. Now, out of all these frequencies, at a certain amount of time, you will be interested in one particular frequency, right? Or you just want a Wi-Fi, not nothing else, or simply two are available or three are available. Selectivity means the receiver must be able to tune into the right frequency. The design must be such that it should be able to select the one that you desire and reject all the others. The frequency should not be mixing or interfering with each other. You must be able to tune into the specific frequency. So that is the selectivity of a wireless receiver. Well, there is another scenario. Now here, these days this work is going on in the industry. You have macro cells, which are traditional macro cells. We have base station and which cover a certain area like maybe 30 kilometers, 35 kilometers. Then you have femto cells. Now, femto cells are inside the building. So we have a macro base station and you have a femto base station here. Femto base station covers a smaller area, maybe a few meters or maybe 20 meters, 10 meters, 50 meters. Now, since the macro cells and the femto cells, they are overlay actually. The same carrier supports the femto cells as the macro cells. Now, it is possible that when you are at the edge or on the macro cell, the smartphone is receiving signals from both the places. It is receiving the signal from the base station as well as from the femto base station. So the one coming from the femto base station for this particular, the smartphone is interference. This is the signal. And for a PC inside the femto cell or at the edge of the femto cell, the signal coming from the macro base station is interference, while the signal coming from the femto base station is the signal. So you must be able to distinguish between the two, that which one I am looking at. Do I need the signal from the base station or the femto base station? Now, usually, what the carrier will do, they will assign different channels or different frequencies for each of these two applications, for the macro base station or the femto base station. But it can be problematic at the cell edge, at the femto cell edge or the macro base cell edge. So in that case, a decision has to be made, okay, which signal should I lock into? Usually there will be a threshold set that if the signal level falls below this level, then I switch to the other one. So if my signal level falls below a certain, let's say the signal level is minus 100 dB is my threshold. So if the signal level falls below minus 100 dB from the macro base station, I must switch to the femto signal. Okay, so there is a question here. Handoff issue is addressed here. No, we are not talking about handoff issue here. That is a more advanced topic. Yeah, so actually the carriers, what will they do? They will have a handoff feature available to you where you can hand off from one cell to the another, from the femto cell to the macro cell, or from the macro cell to the femto cell. But the handoff, what is the trigger for handoff? The trigger for handoff is the signal level. Okay. So I must be selecting the right signal to trigger off handover from one cell to the other one. Okay. Well, so in general, the selectivity of a receiver is determined by the filter response, what type of filters we have, what is the response of the filters. If you write the transfer function of the filter, how many poles are there, how many zeros are there, and that all the transfer function of the filter will determine how steep is the response from the stop band to the pass band. Now here in this example, the response is not very steep. It's just gradually moving from stop band to pass band here, and then falling off again steeply. Now this is a picture of a very simple band pass filter, but it can get more complex. It depends on what type of function you are implementing here in the filter. So it all depends on the design of the RF filter, the response of the filter, and the bandwidth that it allows, the pass bandwidth. Okay, so that determines the selectivity. So the narrower the bandwidth here, the more selective is the filter. If you narrow it down to more, there is very little strip around the carrier frequency. But if your bandwidth is very large, the selectivity will be less. You will be rather selecting a range of frequencies instead of just one frequency. So filter design is very important to determine the selectivity of a wireless receiver. Okay, let's move on to the next topic, stability. Now it must be stable. Our receivers must be stable. There should be no impact of change in supply voltage, temperature, even mechanical vibrations or the environment, any type of environment conditions. So imagine if our receiver design was not stable. These base stations are installed outside in the fields. So they will keep on changing on frequencies. The frequencies will drift from time to time, and you simply cannot provide the service. So this is a very important criterion. See, for industrial grade base stations and receivers, they are subjected to all these type of tests actually in the factory. They are subjected to environmental conditions, temperature conditions, and even various supply voltage, that nothing drift the frequency. The frequency should be rock solid at whatever it's supposed to be. Now, spurious responses. Now, inside the receiver architecture, we see there are several blocks here. You have RF filters, you have demodulators, you have automatic gain control, you have IF amplifiers, local oscillators. Now, you know, all these are implemented in discrete components, in hardware components. They generate their own spurious frequencies too. Like a local oscillator, though we tune it to a frequency f0, it might generate twice f0 and thrice f0 and so on. You know, there's no ideal oscillator will generate only one particular frequency. So we have to somehow deal with that. We have to suppress any extraneous or spurious responses inside the receiver. There could be image frequencies. Now, image frequencies are typically, we'll dwell on this a little more in detail in another slide. When we have IF intermediate frequencies inside the receiver, you know, it's like listening. Okay, let me give you an analogy. When you're tuning into an AM radio, sometimes you listen to two stations at the same time, right? So you are tuned to one station, but the adjacent station is so nearby that it interferes with your reception. So something similar happens here. If you don't reject image frequencies, you could be getting two stations at the same time, and that could interfere with your data in this case too. So we have to reject image frequencies which inside the receiver too. Now, phase noise. You know, when the signal propagates through space, or even when it travels through the RF filters and so on, there could be a phase change in phase actually. That is called phase noise. Now, phase noise becomes important for digital modulation techniques like QAM, quadrants amplitude modulation, which is used in wireless LANs, in LTE, and so many other wireless broadband technologies. They are very phase sensitive. There is a limit to how much of phase drift they can support. So phase noise is also very important characteristic here. We have to know how much of phase noise our receiver can tolerate. So it can interfere with the detection process in the phase sensitive modulation techniques such as quadrature amplitude modulation. Okay, spurious frequency dynamic range, which is nothing but the ratio of the strongest signal to noise flow. You know, we have talked about a very weak signal here so far. So we have sensitivity, and then we have all that stuff. But you know, a very strong signal can also create problems. A very strong signal can cause overload in the amplifiers. So we have to know what is the limit. What is the limit of the signal? How much of strong signal we can tolerate in the receiver? Now here in this illustration, we are showing overload of minus 30 dB. So the difference between this overload level and the noise floor is the SFDR, the spurious frequency dynamic range. Now, why we call it spurious frequency? Because when the signal grows to this level that causes overload, it causes a drift in the signal overshoots into the non-linear region of the power amplifier. So those of you who are familiar with the RF power amplifiers, you remember, like if the input signal goes beyond goes into the non-linear region of the amplifier, we'll have distortion, we'll have harmonics and all that stuff. We'll have spurious frequencies generated inside the receiver. So that is why this criteria is important here. We have to know what is the SFDR, how much of strong signal we can tolerate inside the receiver. A very strong can cause distortion and third order harmonics, which are spurious responses, and those can interfere with our normal detection process. Well, automatic gain control. You know, it's a very simple function, well, but very important one. It has to maintain a constant output level over a wide range of input signal level. You know, input signal level can change from very weak to very strong, or somewhere in between. So what that means, that it could cause a very inconsistent response from the amplifiers. So the AGC block here, automatic gain control, it takes an input from the baseband signal output and adjusts the amplification of the IF amplifier. That is called automatic gain control. It's very common in even traditional analog radios like AM and FM radios. They always have an AGC implemented inside to keep the signal level constant. Now let's pause for a while and try to answer this question. Selectivity of a receiver is determined by the RF filter response. Okay. phase noise is of no consequence to QAM receivers. Narrow RF filter makes a more selective receiver. Extremely strong signal at the handset can generate third order harmonics. So just take a second and think about this, like which one is correct out of these. Okay, very good. There are some responses here. Okay, let me go through this. So selectivity of a receiver is determined by the RF filter response. Well, yes, that is true. Phase noise is of no consequence to QAM receivers. No, that is false, because we just saw that phase noise interferes with the detection process of a QAM receiver. So narrow RF filter makes a more selective receiver. That is true. Extremely strong signal at the handset can generate third order harmonics. That is also true. Okay. Let's move on to the next slide. Now we are moving on to the receiver topologies, the different receiver architectures which are used. So starting with the traditional super heterodyne receiver, which is conventional, and in conventional radios also this is there. The AM, FM, and SSB radios all use super heterodyne architecture. Now what it basically does is it down converts the received frequency to an intermediate frequency. The IF is called an IF. Now what happens with that? We distribute gain between the RF and IF stages. You know, we have an RF amplifier here, but then when you down convert using this local oscillator, you have an IF filter, you have IF amplifier here. So we have signal gets amplified in two stages, RF amplifier and the IF amplifier. Now what that means that we don't need to have a single large amplifier of very high gain, because that is not efficient and it can create more powers. We distribute the gain between two stages, RF and IF, and that also makes it more stable, because high gain amplifiers can cause instability too, as we've seen before, that if the input signal overshoots into the nonlinear region of the amplifier, it can cause harmonics, distortion, and so on. So to keep that in check, we distribute the gain in two stages, RF and IF. Well, now before we move on, it's just a list of different modulation techniques that have been used in the past. So for analog signals, we have used amplitude modulation, AM, frequency modulation, FM, phase modulation, PM, or single sideband. Then for digital signals, which are more prevalent in cellular communications, these are the various modulation techniques. Amplitude shift keying, ASK, which is very basic one. Pulse modulation, pulse amplitude, pulse width, or pulse position. Quadrature phase shift keying, QPSK. Vestigial sideband, 8VSP. This is used in high definition TV, the digital TV transmission. Quadrature amplitude modulation. This is of interest to us in the cellular communication world. And then we have the OFDM and the direct sequence spread spectrum. So you know, we have so many different techniques based on application, and one set for analog signals and the other set for digital signals. So here we are more focused on the QAM and how it works, and OFDM and DSSS. This is more relevant to our LTE and WiMAX and wireless LAN and other cellular communication technologies. Okay. Now there is an example of a super heterodyne receiver that we saw the architecture before. Now this is for a frequency band of 902 to 928 megahertz ISM band UHF receiver. This is an amateur band and used in an unlicensed band, used for many mobile applications. Well, you see here that the ISM band, the modulation is FM. The bandwidth of around the carrier frequency is 50 kilohertz here. Now here, you see, if you notice the local oscillator frequency range, this is from 874 to 900 megahertz. Why is it like that? You know, our incoming signal could be between 902 to 928 megahertz. We have to keep a difference of the IF frequency. Our IF is going to be 28 megahertz here. So at a distance of 28 megahertz, we generate frequency in a local oscillator. And what happens inside the mixer? Our signal, the carrier frequency comes in from this side, and our local oscillator at a distance of 28 megahertz comes from this side. This is a product mixer. Product means we just multiply the two signals. In the output, we get a different signal which is at 28 megahertz, which is of interest to us. We reject everything else, but we just get the 28 megahertz IF frequency. So you know what we have ultimately done? From 902 megahertz, we have brought down the frequency to 28 megahertz. So that gives us benefits. We distribute the gain, as we said before, because we can now filter this frequency out 28 megahertz and amplify it once more. So we have a second amplifier here, 28 megahertz, and after that we have a discriminator or a detector that takes out the baseband signal from the FM signal that is received here. Now, what is the image frequency here? I've given one box here to make it more clear. Now, you know here, like, let's take this 928 megahertz. Now, 928 megahertz is at a distance of 900 megahertz from the local oscillator. That gives you a different signal of 28 megahertz. Now, what if we have another carrier frequency or another receive signal which is at 28 megahertz less than 900 megahertz, like which is at 872 megahertz, which is at basically twice of the IF. So 928 minus twice the 28 megahertz gives you 872 megahertz. Now, if we also had 872 megahertz signal coming here at the mixer, that will also produce a different signal of 28 megahertz, right? So we have 928 minus 900 gives 28 megahertz. But 900 minus 872 megahertz will also give us 28 megahertz. So that is the image frequency. It is the image of this particular received signal. This is the desired signal, right? 8 megahertz. But we have an image carrier frequency of that we know 872 megahertz. We must reject this signal out at the RF filter itself. So now you know here what we are doing. Our RF filter has a band pass of 902 to 928 megahertz. So 872 megahertz is outside that range. So image frequency gets filtered out at the front end itself. It does not even enter the mixer. So we will not have the problem of two stations listening at the same time. We have only one station here, which is coming from 9 megahertz. And the one that come, like if we were not careful here, if we were not rejecting out 872 megahertz here, we could also get another signal of 872 minus 900 megahertz, 28 megahertz here. So this is very important. Whenever we design the IF stage of a super heterodyne receiver, we have to consider this. We have to consider, are we able to reject image frequencies or not? Because image frequencies can be a nuisance. That will undermine the selectivity of the receiver itself. Instead of selecting one carrier frequency, you are selecting two. If you are not careful, if you are not rejecting image frequency out. So I hope I have clarified this. If any question, you can ask me. Well, this is going to a next step. We also have double conversion super heterodyne receivers. Now this is an example from 450 to 470 megahertz UHF businessman receiver. It's a double conversion. Why it is double conversion? Because instead of one IF, we have two IF stages. You know, first IF is at 28 megahertz here, and the second IF is at 10 megahertz here. So what is the benefit of having two IF stages? Now here, you know, this is a higher frequency, 28 megahertz. So remember, if the frequency is higher, our passband is also higher. So it is less selective. But we add another IF stage of 10 megahertz that brings the frequency even more down, brings it down, and it reduces the passband also, the size of the passband. So it makes it more selective. So the benefit we get from multiple IF stages is we improve the selectivity. We improve the selectivity of the receiver here. We become more selective. And again, we have to be careful here how we select the IF frequency here. For here, in this case, like we have 442 megahertz for the upper limit of the local oscillator, and then we have 470 megahertz. Difference of these two gives us 28 megahertz. But what is the image frequency of 470 megahertz? The image frequency is 414 megahertz, and 414 megahertz outside the filter range. So 414 megahertz will be rejected right here at the front end. So we only have one. We don't have any possibility of receiving a image signal here, which could interfere with. We have only one station. We are having only one station here, 28 megahertz. And at the second mixer, again, the simple formula to calculate is you subtract twice the IF. So 28 megahertz minus twice the IF. Twice the IF is 20 megahertz. That gives us 8 megahertz. So 8 megahertz again is outside this range. We are filtering only 10 megahertz carrier frequency of 10 megahertz centered at 10 megahertz with a bandwidth of 15 kilohertz around it. And then we go to the second IF amplifier stage and then a discriminator. So the expensive super heterodyne receivers always use multiple stages because they improve the gain. You know now how many amplifiers you have? You have an RF amplifier, you have first IF amplifier, and the second IF amplifier. So you have 3 amplifier stages. That gives you more gain, and it makes the receiver more selective too. You can simply narrow down to the right frequency that you want to hear. Okay. So let's move on to the next slide here. Now coming to the direct conversion receivers, which are of very great interest to us because of their application to digital modulation techniques and all our cellular communication technology and the wireless broadband. So in direct conversion receivers, we do away with the IF. We have no IF. It's zero IF. There is no intermediate frequency. Yes, that is why they are also called homodyne. Since there is no IF, we cannot do any automatic gain control too, right? The only amplifier is in the front end. Now in this case, the application is usually in the digital modulation, QAM, quadrature amplitude modulation. Why? Why is that so? Because we lose the benefits of high gain and selectivity here. This is, it looks very simple to implement and very cost effective. You just have a modulated signal input, we have a passband filter here, you have RF amplifier. You mix it with the local oscillator, which is at the same frequency as the received carrier. You just get a baseband signal out here. No more IF demodulation and so on. Another low pass filter, you have a baseband amplifier and a quadrature detector because you're using QAM here, and you have a digital signal processor. So what happens here? What is the benefit of this? Benefit is, of course, it's very simplified, low cost, but we have challenges. How do we make up for the lost selectivity and the lost gain advantage that we had with super heterodyne receivers? So here we must have a digital signal processor, a DSP. We use DSP techniques to retrieve the signal to make it more selective and to have gain. So digital techniques help us to overcome those benefits that we have lost. And that is why these direct conversion receivers find a lot of application in the modern wireless receivers. Modern, I mean by modern, is the cellular communication receivers, the LTE receivers, the wireless LAN receivers, all of them have direct conversion receivers. Because it's more cost effective and because the processor is readily available in these devices, in the handsets. The older radios didn't have a processor. See, your car radio may not have a processor. It is just an analog AM or FM receiver, that's it. But in the case of handset, you already have a processor inside and you can implement DSP techniques to compensate for gain, selectivity and other benefits that we earlier had with super heterodyne receivers. But the benefit is we make it more affordable, more cost effective and more applicable to digital communications. Okay. Let's pause for a while and try to answer this question. Well, which of the following is correct? AM and FM broadcast receivers are generally direct conversion receivers. No, they are not. Cellular and Wi-Fi receivers are generally direct conversion receivers. Yes, they are. Super heterodyne receivers are highly selective, have high gain and stability. Yes, that is true. Direct conversion receivers are generally best for AM, FM, VHF and UHF broadcast reception. No, that is not true. Our conventional AM, FM, VHF, UHF, they don't use direct conversion receivers. They have been using super heterodyne receivers. Well, the story may be different with the high definition TV. HDTV broadcasts are direct conversion receivers. Why? Because they use the same techniques. The vestigial sideband, VS8 VSB, which is similar to quadrature amplitude modulation. So if you use those techniques, the digital modulation techniques, then of course, then you will use a direct conversion receiver. But the conventional receivers, they all use super heterodyne receivers. Okay. Any questions so far? You can ask me. Let's move on to the next one. Now let's move on to the topic of interest to us, the quadrature amplitude modulation. Now this is why we call it QAM. Quadrature means it's a phase difference of 90 degrees between the two signals. It's a quadrature. Then we use amplitude. We also use the amplitude of the signals to determine the state, the modulation state. Since it's a combination of amplitude and phase modulation, it has many flavors. 2QAM, which is called BPSK, binary phase shift keying. 4QAM, which is called quadrature phase shift keying, QPSK. 8QAM, 16, 64, 256, 1024, 4096. Now, what is the meaning of all these numbers actually? 2, 4, 8, 16. These are the number of states that QAM modulation technique can handle. And in this table, it also defines the bits per symbol. How many bits you are able to transmit in one symbol? Now, what is one symbol? Means one transition in amplitude or phase. One combination of amplitude and phase. That is one symbol. So, like 2QAM can carry only one bit in a symbol. So, one bit means it can be either 1 or 0. So, there are two states here. 4QAM, you have 2 bits per symbol, but so total of 4 states. 2 bits, you could have 0, 0, 0, 1, 1, 1, 1, 0. So 4 possible states. 8QAM, you have 3 bits per symbol, that you can transmit, but you have 8 states. So your number goes on exponentially here as a power of 2. Typically, as an example, LTE and wireless LAN, it's very common for them to use 64 QAM. That means in just one symbol you have 6 bits, and you have 64 states. 2 exponent 6 is 64. Well, you could go even higher, but as you go higher in the number of states, the modulation and demodulation becomes more challenging. Because you have so many states, you have to figure out so many states, and you need more and more powerful electronics and sensitivity and DSP processors and new algorithms to implement to be able to determine each state from to differentiate the states as the number of states increase. Well, so basically, just to simplify QAM. So any QAM signal will have actually 2 signals: in phase signal, which is I, represented by this horizontal axis, and a Q, which is at a 90 degree, a perpendicular axis. So there is a phase difference of 90 degree between the 2 signals, between I and Q. That is why we call quadrature. Quadrature means 90 degree. Then, how do we present the amplitude and phase combination? These dots here, 0, 0, 0, 1, 1, 1, and 1, 0. These are the states. So each state has a location in the constellation diagram. Now the diagram I'm showing you, this is called the constellation diagram. So for any QAM technique, we always need to have a constellation diagram, and each state need to have a location in the constellation diagram. The location determines the amplitude. Like 0, 0, its distance from the origin is the amplitude of that state, and phase is the angle it makes with the eye. So amplitude and phase. And since every state has 2 components, if you draw projections on the I and Q axis, so the projection here gives you the I component, and the projection here gives you the Q component. So any state in a QAM has 2 components, I and Q, which themselves are at 90 degree to each other, but the location of the state within the constellation diagram gives you the amplitude and phase of that particular state. So for example, for this example, this is a 4 QAM, because there are 4 states here: 0, 0, 0, 1, 1, 1, and 1, 0. So you have a 4 QAM constellation diagram represented here. Now, same way we can. Okay, before we look at the next slide, this is a more physical representation of the signals. So if you see the signals on the scope, you will see them like this: the I signal and Q signal, 2 sine waves. Actually, this one is called sine and this is called cosine, because why is it called cosine? Because it's at a phase difference of 90 degrees. The peak of this is at a phase difference of 90 degrees from the I signal. So this is how the signals will be actually physically transmitted. And each of them will have 4 states, which is a combination of amplitude and phase for each of them. Well, here we go a little higher. We have 16 QAM constellation diagram. So you have 16 states here. So 16 states means we have 4 bits. Each state represents 4 bits. And in the location in the constellation diagram represents their amplitude and phase. So for each of the states, you can draw a line from the dot to the origin, to the center of the axis, and that will give you the amplitude, and the angle it makes with I is the phase. Okay, and then you can determine the 2 components I and Q by drawing projections. Projection here gives you the I component, and the projection on the vertical axis gives you the Q component. I hope this is a little clear. If any questions, please ask me. Okay. Now we discussed before that the quadrature amplitude modulation or any digital modulation techniques, they are susceptible to phase noise. Because here you have what you have. You have amplitude and phase. So they are also susceptible to phase noise. Now, in order to determine what is the impairment caused in QAM by phase noise, we define a parameter called error vector magnitude, EVM. It's also called receive constellation error. This is simply a measure of modulation impairment. What happens when you have phase drift in either the I or the Q component? The location of the state changes. Now this is the ideal symbol here, the one shown by the arrow here, and because of the phase noise or the drift in phase, the location of the symbol will change from this to here. This is just the outline, non-ideal symbol. So ideal symbol is here, but the non-ideal symbol is shifted to here. So when you actually receive your QAM signal, you might find that your symbol has shifted in phase. Actually, there is a phase drift of phi. Now, the error vector, we should draw a tangent from the ideal symbol to the non-ideal symbol. The tangent here, the magnitude of that tangent is the error vector, and that helps us determine the error vector magnitude. So it's simply a measure of how much of phase noise or impairment is present in QAM. Okay. So mathematically, we take it like this. We take it as a 10 log of ratio between the RMS power of the error vector and the reference constellation average power. So if you are using any equipment to measure phase noise, this is how they will mention a EVM in dB, that this is the error vector magnitude in dB for this particular signal. Well, now this is a very simplified block diagram of a QAM modulator. So in QAM, like we have seen, that we need two signals, I and Q, which are at 90 degree to each other, and their respective combinations of amplitude and phase will give us the different states, and each state represents a definite number of bits. So here so when you modulate, you get two streams of data, the I channel data and the Q channel data, right? Because we ultimately get a combination of two signals here in the output. So I channel data is data, and then you convert to analog. Then there's a local oscillator. Now here, notice this: the local oscillator, you supply one signal direct to the I channel mixer, and there is a 90 degree phase shift network here, which shifts the phase by 90 degrees to generate the Q signal, and then it mixes with the analog Q channel data here. So that is how you generate the I and Q signals. One of them, the Q signal, is 90 degree phase shifted. Finally, you just combine here and combine them together, and that gives you an RF output here. Well, there's a question here: are I and Q already 90 phase shifted? Well, they are phase shifted here when in the mixer, actually. When you apply the local oscillator, a 90 degree phase shift signal, that is when you shift, actually. Previously, you just have two streams: I channel data stream and a Q channel data stream. So the first one is only data. This is not yet analog signal, actually, right? This is again not yet shifted. You have to actually shift the signal by having a 90 degree phase shift network. So we are not doing it again, actually. In the previously, we are only separating the two streams. Which data will go into the I signal and which data will go into the Q signal. It is not actual signal which is phase shifted. Phase shift happens here when the local oscillator frequency is phase shifted by 90 degrees. That is how we get the cosine signal. Okay. So then finally we combine it. We have combination of I and Q signals, and that gives you the RF output. Okay. Demodulator, when you demodulate the QM signal, it's the reverse process. So you have the RF input here. So again, you have a local oscillator. You apply a 90 phase shift signal here to get the signal out, and you just convert from analog to digital in the final output. And finally, you get the I channel data and the Q channel data, which you can process further to make sense of it, to make a single serial bit stream. So there's one more question here: how we decide the data to be sent to I and Q? This is like when you determine the states, right? So you draw a projection there. Then you determine which one is I data and which one is Q data. Right? Okay. So now let's talk about a little more the spread spectrum technique. Now, spread spectrum technique has been used in many technologies. Typically, CDMA uses this, and many other technologies also use it. So what is unique about spread spectrum? We spread the signal over a wide band. In the illustration you see, previously we have a narrow band signal, a narrow bandwidth of a typical bandwidth here. We spread it out and make the bandwidth wider. Now, what is the benefit of increasing the bandwidth of the signal? What do we get out of it? It provides more frequency diversity. That means we have resistance to fading effects. If we had a narrow band, and if this single narrow frequency were to fade, we will lose all the signal. But in case of wide band, it's possible that because of a wide band, we won't lose the whole signal, only parts of it. So let's say we part of lower frequency might fade and a part of high frequency might fade, but we still have most of the signal with us, and we can easily reconstruct through various techniques the remaining lost signal. So that is the benefit. We get frequency diversity, we get resistance to fading effects, and moreover, this signal appears as noise to non-SS receivers. We'll see in the next slide how that happens. So if it appears as noise to non-spread spectrum receivers, That means nobody can intercept unless they need the PN key, or unless they know the code of our signal. So it is resistant to interference and anti-jamming effects, and primarily two ways of doing it: frequency hopping spread spectrum, FHSS, and a direct sequence spread spectrum, DSSS, right? Okay, let's move on to the next slide. There is one parameter here we use for spread spectrum, a processing gain and a spreading factor. So this is simply nothing but a measure of how much we're spreading. So from narrow bandwidth to wide bandwidth. So spreading factor is a ratio of the spread bandwidth to the unspread bandwidth. It just gives us a measure of how much spreading we have in our spread spectrum signal. And then another way of saying it is in dB, which is called processing gain, and it's 10 log of the ratio of spreading factor. So whenever you come across an implementation of spread spectrum, maybe CDMA or something else, there could be some mention, okay, this is a spread here, this is a spreading factor here. That will give you an idea that how much of bandwidth we are spreading. Now in a FHSS, frequency hopping spread spectrum technique, what we are doing, we are actually hopping the frequency. You know, in the unspread signal, we have a single narrow frequency here, but at the output you see we have a spread signal, which is very wideband. And what we do, how do we achieve it? We just hop from one frequency to another. So that is how we cover the whole band. So how do we do that? So in the local oscillator, we have a frequency synthesizer and a PN code generator, which hops the frequency, which changes the frequency of the local oscillator actually. We do have data in coming from here from a frequency shift keying modulator and the intermediate frequency, which is low down the IF, and then coming to mixer here. But we hop the frequency in the local oscillator. So the output signal will not have a constant frequency. It will be hopping from one frequency to another. And it hops frequency according to a certain PN code, a pseudo-random noise code, which has to be known at the other end of the receiver to retrieve the actual signal. Like we see on the receiver side, we do the reverse. We have a band pass filter for the wide band. And then in the mixer, we use the same PN code that we had at the transmitter, hop the frequency again, so that we retrieve the B-spread signal, which is very narrow band, and we get the data out. So frequency hopping seems very simple technique, but yeah, of course, you need a PN code generator, just hop the frequency and you get the signal out. But it has its own limitations too. Now, you know what happens when you hop the frequency, we change the frequency according to PN code in the frequency synthesizer, it cannot maintain phase coherence. Remember, the phase is very important for us for quadrature amplitude modulation and for any digital modulation technique. So phase coherence is not maintained. So that is why we cannot use QAM with FHSS. With FHSS, we cannot use QAM. We have to use frequency shift keying or multiple level frequency shift keying or things like that. We cannot use QAM because phase coherence is not maintained when we hop frequency. So that is why FHSS does not find use in CDMA techniques or any other spectrum techniques. Well, PN code is just a random code used to create local frequency. But what decides frequency is that how many times we hop the frequency. So how wide is our band? What is the range of frequencies we are hopping? That is what decides the bandwidth. So PN code itself is just a code, a random code which used to hop from one frequency to another. But how many frequencies you actually hop, that decides the frequency, the bandwidth. So as I just said, like FHSS, we cannot use QAM in this because of the incoherent phase from one frequency to another. Okay, so there's a question, why not QAM again, please? So, in quadrature amplitude modulation, we have to maintain a very strict phase difference between I and Q signals. We have seen that before. So phase is very important. Phase coherence has to be maintained. The phase should not change actually. We have seen that what phase noise can do. But here, when we are in case of FHSS, because we are hopping from one frequency to another, suddenly changing frequency in the oscillator, like now it is 1 megahertz, next time is 5 megahertz. So switching from one frequency to another, we do not maintain phase. The next frequency we choose may be starting from a different phase angle actually. I'm sorry. So since we are not maintaining phase between the frequencies, because that is a tough challenge to achieve actually, the frequency synthesizers cannot maintain phase when they are hopping from one frequency to another. So that is why we cannot use QAM. QAM cannot be used because we don't know at what phase angle the new frequency will be starting actually. We are stopping one frequency and starting another angle. So that is the reason we cannot use QAM. But despite that, it still finds use. So FHSS technique finds use in some machine-to-machine communications. Machine-to-machine communications, which is an intensive area of research these days. It's intended to connect the devices together. Now there, the requirements are different. We don't have the same requirements as in cellular communications. So there, FHSS finds uses because there the reliability of the signal or information that is sent is more important. It's more important than the bandwidth or the data rate and other things. Defense work, yes, in defense work too, because you need a very 100% secure and reliable communications. Whether it's fading or not fading, whether it's raining or not, you must be able to transmit data. That it can be achieved by frequency hopping. That you make the band very wide and hop the frequency so that at some frequency you are able to transmit actually, right? So that is why commercially it's finding use in machine-to-machine communications. In fact, there is a protocol which is already validated by the Federal Communication Commission. It's called weightless. The weightless protocol has selected FHSS technique and frequency shift keying and MFSK for machine-to-machine communications. Okay, let's move on to the next one. This is the more commonly used in CDMA, the direct sequence spread spectrum. So here, what we do, instead of hopping the frequency in the oscillator, we expand the bandwidth in a different way. We just have, this is a data pulse here with amplitudes of +1 and -1. It could be volts or something, or minus or microvolts or millivolts, whatever you can call it. So this data stream is multiplied with a PN code. PN code is again a range of pulses. It's also called the chips. It's also called the chips. So like in typical example here, we are using 24 chips per data symbol. So for each data symbol, we are using 24 chips to expand the bandwidth. Where we multiply data stream with the PN code pulses, we get the output signal, which is what? Which is a wideband signal. You see, instead of this slow bit rate, now we have a very fast changing pulses here, which means higher bandwidth. So that is how we increase the bandwidth in case of DSSS. We multiplied the data stream with the PN code directly, then the output we get is a wideband signal. So here again the same things apply. Spreading factor here is the ratio of chip rate to symbol rate. In this example, it's 24, and the spreading factor also means the bandwidth is spread 24 times compared to unspread bandwidth, and the processing gain we can calculate here is 10 log of spreading factor, which is 13.8 dB here. Okay, so here because we do it differently, we expand the bandwidth in a different way. It is possible to maintain phase coherence. So we have in a mixer, typically we have data in here. This is the unspread signal. We have a PN code generator here, which mixes with the data in, which is a product. This is the product mixer actually. In the output, we get the signal here, which is wideband signal. And finally, we have a QAM modulator here, which gives us the RF out. And this is the spread signal. So because of phase coherence maintained in this type of technique, the DSSS, we are able to use this spread spectrum technique in CDMA. CDMA uses DSSS. And many other wideband CDMA techniques too. So there we can use QAM and other techniques. So DSS receiver, this is the reverse of the transmitter. You just get the modulated signal in, demodulate with the QAM demodulator, and then inside the mixer, we apply the same PN code generator, take a product of it, the difference of it gives us data out, the baseband signal out, and that is the D-spread signal here. So where is okay, there is a question here. How does it increase bandwidth by just multiplying with PN? Okay, let's go into a little more detail. If you take a Fourier transform of a low bit rate data signal, in the output you will see low frequency components. But if it is a high bit rate data signal, that is actually a combination of high frequency components. So high frequency components, that means more bandwidth. You have more frequency components, ranging from low frequencies to all the higher frequencies. So any bit stream or data stream can be represented as an equivalent of components of frequencies, right? So, and that is true. You can do a Fourier transform and transform it to a higher. So higher bit rate means higher bandwidth, and lower bit rate means lower bandwidth. As a thumb rule, we can just see that. But mathematically, you can show that, you can prove that, and you can prove it in the lab also. So multiplying, okay, let's go back to the previous slide where we do the multiplication so that it's more obvious here. Here in a low bit data rate, so how many you have only, this is here 24 times. The PN code is 24 times here. So that means we are increasing the bandwidth by 24 times. We are putting in more frequency components. We are changing it faster actually. Higher frequency means we are changing faster actually, right? And lower frequency means we are changing slower actually. So this looks like a square wave or a stream of pulses, but it's actually a combination of different frequencies. And by doing a Fourier transform, you can prove that it's a combination of higher frequencies, so higher bandwidth. Does that make it clear? Well, it may not be very intuitive, but yeah, if you think it that way, yeah, it is the higher bit rate means higher bandwidth because it's equivalent of a combination of higher frequency range. So your bandwidth is increased that way. Well, okay, let's pause for a while. Which of the following is correct? FHSS is best for QAM. DSSS expands the bandwidth of signal. Higher the phase noise, lower will be the error vector magnitude for a QAM signal. Most wireless broadband applications use QAM. You could choose multiple answers too. It depends on which one you think is correct. So the first one is not correct. FHSS is not best for QAM. We have seen that because there is no phase coherence maintained, so QAM cannot use FHSS. D expands the bandwidth of signal. Yes, that is true. By multiplying with the PN code, yes, we can do that. So higher the noise, lower will be the EVM for a QAM signal. No, that is not true. Higher the phase noise, more will be the error vector magnitude actually. EVM is a direct measure of the phase noise. So 3 is not true. Most wireless broadband applications use QAM. That is true. Let's move on to the next slide, which is about the OFDM, orthogonal frequency division multiplexing, OFDM. Now, OFDM is essentially a multi-carrier modulation. Here we go one step further. Instead of using just one carrier frequency, we use many carrier frequencies. And then we'll see what are the benefits of doing that. Now, all these subcarriers, they are called subcarriers, right? Because you have multiple carriers and we give it a name, we call it subcarriers. All these subcarriers are orthogonal. Now, what is the meaning of orthogonality here? That means they are mutually exclusive. I mean, not interfere with each other. This is contrary to our traditional thinking. Like, okay, if one carrier is very close to the other one, it can cause interference through image frequency and all that stuff, right? But here we are going a step further. We are using orthogonal subcarriers. How do we achieve that? We maintain subcarrier spacing in a very consistent manner. The subcarrier spacing, which is actually the bandwidth between two subcarriers, we maintain it in such a way that the peak of one subcarrier coincides with the null of the adjacent subcarriers. As you see in the diagram, the peak of one subcarrier coincides with the null of the adjacent subcarriers. So this is very important. We have to maintain a very consistent subcarrier spacing to achieve orthogonality in case of OFDM. So all the subcarriers, they must be strictly spaced apart in such a way that the peak of one coincides with the null of the other. If that is the case, then this subcarrier, although it overlaps with the adjacent one, it will not interfere. It will not interfere with the adjacent subcarrier. So that is the key to orthogonality here. That is why we call it orthogonal frequency division multiplexing. It is frequency division because why frequency division? Because we are using so many frequencies. F0, F1, F2 and so on F1. Typically, there could be thousands of them, there could be hundreds of them, or there could be even more. So the more frequencies we have, the more is the bandwidth here. So multiples of a subcarrier over an integer cycle and subcarrier overlap is allowed, as we have seen. Peak of one subcarrier occurs at nulls of the other subcarriers. That is the key to orthogonality here. Well, what are the benefits? See what we can do with when we have multiple subcarriers which though overlap with each other but they do not interfere with each other. We can transmit parallel streams of data. So this is our incoming serial data stream, which maybe it's very high. From the picture it looks like it's a very high data rate. It may be 54 megabits per second or 100 megabits per second. So what we do here, we split this data rate into multiple subcarriers. So we have parallel data streams here which are much slower than the original. This was very high, it was 54 megabits per second. Now here it could be only 1 megabit per second and so on, or even less than that. So it's like, having many parallel lines transmitting data. So parallel lines can carry more data actually. The data rate on each particular parallel line is much slower because that is the capacity. But by combining these parallel data streams, we are increasing the bandwidth of the overall channel that consists of multiple orthogonal subcarriers. So that is the reason we have high spectral efficiency. What is spectral efficiency? That means how many megabits per second we can transmit per hertz. So it has high spectral efficiency compared to many other modulation techniques. High data rates can be achieved with several parallel low data rate subcarriers. And this is a very important key technology used in all wireless broadband technologies, whether it is wireless LAN, WiMAX, LTE, or wideband CDM. We use OFDM. OFDM is the key to that high bandwidth. How do we get 54 megabits per second or even 100 megabits per second? By using multiple subcarriers which are orthogonal to each other and which carry parallel data streams. Well, there is another benefit of doing that. Since each subcarrier is a very narrow frequency band, So in this illustration, we see the normal signal which is not faded. But here we have specific components of subcarriers. They are fading actually, but they are flat faded. That means each frequency we can equalize at the receiver end. So our equalization becomes very simple. For each frequency subcarrier, we just have to bring it to the right level of signal. That's it. Unless if we do not have orthogonal subcarriers, we will have a very wide band. But then parts of the band will be faded and parts will not be. There it is more of a challenge. The electronics and the processing becomes more challenging in that case. But in this case, it's very simple. We simply have to switch each frequency subcarrier to the same level, so that finally we mitigate the fading effects. So equalization becomes very simple in case of OFDM. So here we have a question. Here we reduce the bit rate, then how can we save increased bandwidth? Okay, let's go back to the previous slide. Here, when we say bandwidth, we say bandwidth of the complete OFDM channel actually, all the subcarriers included. So you add up the bandwidth of each subcarrier, that gives you total bandwidth. So we increase bandwidth, the total bandwidth actually, not the bandwidth of one particular subcarrier. So total bandwidth is much more. It may be 20 megahertz, 25 megahertz, or 40 megahertz. But each subcarrier occupies only very small band because it's carrying very low data rate. Okay, next question we have: as perturbation increases, this technology lose the interest. I couldn't. Can you please clarify this question? I mean the OFDM. Well, right now OFDM is the hot one. Yeah, in future you may have. You don't know what will happen in 5 years from now, 10 years now. Some smart people, maybe some of you, one of the people here in the audience, may come up with a new modulation technique which is even better than OFDM. But as of the current research and current application for wireless broadband, OFDM is the one. Did I answer your questions? Please let me know. Okay. Parallel flat fading subcarriers, simplify. Okay, there's another question. Since we need to put filter method which decrease the bandwidth, well, yeah, then you have to design your filters accordingly, When you design a filter, then the first criteria is how much bandwidth you need. This bandpass filter will pass how much of bandwidth. So you have to design the filter accordingly. It's depending on how much bandwidth you need, and accordingly you design the filter. Yeah, your concern is valid. Your filter design will be critical here. Okay, so now OFDM is also resistant to effects of multipath fading. So why it's resistant? It has low symbol rate. Low symbol rate means, see, this derives from our low data rate. Each subcarrier carries a much lower data rate. So our symbol rate is low. That means our symbol duration is high. That means our information in the symbol stays for a longer time over the channel. If that is the case, it will reduce multipath effects. It's resistant to inter-symbol interference, ISI. How do we achieve that? How do we make it resistant to inter-symbol interference? We put a cyclic prefix or CP or a guard interval in front of each OFDM symbol. Now we'll talk about this in a little more detail. In this illustration, this is non-OFDM symbols where there is no cyclic prefix. So there can be inter-symbol interference is expected here. But here, in case of an OFDM symbol, what we do, we make a copy of the tail end of the symbol. So this is the OFDM symbol. Now this variation in the signal here represents one symbol. So at the tail end of the signal, we copy this part of the signal and make a copy of it, and we add it as a cyclic prefix in front of the symbol, which in fact is the guard interval Tg. So original symbol duration here is T0. We make a copy of the tail end of the symbol, which is equivalent to the guard interval, and fix in prefix in front of the symbol. This is called the cyclic prefix. Now here I say that guard interval must be longer than channel delay spread. Now what is channel delay spread here? Now in case of multipath fading, what happens? You have multiple signals coming, multiple copies of the signal. There is a line of sight signal, there is a signal reflected from a hilltop, a signal reflected from a building. So the difference, the time difference between the earliest copy of the signal and the latest copy of the signal, like earliest copy could be a line of sight signal and the latest copy could be reflected from some hilltop. So the difference of time interval between the earliest copy of the signal and the latest copy of the signal, that is called the channel delay spread. And this is a very important parameter in determining what should be length of the guard interval. So then it could change from cell size also, change according to cell size. If there is a smaller cell, then the delay spread will be smaller. If there is a large cell, a macro cell, maybe hundreds of kilometers or 50 kilometers, then the delay spread will be more. So accordingly, we have to adjust our length of the cyclic prefix. So once we have this cyclic prefix in place, what we are doing, we are copying a part of the information which is already present in the symbol and putting it in front of the symbol. So there is redundancy in the symbol itself. Even if at the head end or the tail end we lose part of the signal because of inter-symbol interference, still we have a copy of it available. This will reduce inter-symbol interference. Now there is a question here: why we use CP, cyclic prefix? No, it is not to reduce distortion; it's to reduce the inter-symbol interference. As I said, the channel delay spread is the length of time between the earliest signal and the latest signal. Because of multipath fading, we are receiving multiple copies of the signal arriving at different times. First, we receive the line of sight signal, and then we receive, after a few microseconds, we receive a reflected from the hilltop. A few microseconds later, we receive a signal from the building. They are the same signal, but they are arriving at different time intervals. So in order to cover that time interval, which is causing problems for us, the inter-symbol interference, we put a guard interval. Guard interval is the actually cyclic prefix. So this putting a cyclic prefix in front of the OFDM symbol helps us reduce inter-symbol interference. Inter-symbol interference between different copies of the signal. Okay. Now here, this is a little illustration trying to show here that how this thing happens. Now in case of non-OFDM symbols, there is no prefix here. So you have all these symbols overlapping, coming from path 1, path 2, and path 3. So here you see both symbol 1 and symbol 2, they are overlapping with each other. So you will lose your data or information because there is inter-symbol interference. Whereas in case of OFDM symbols, you have a cyclic prefix, which is a repeat of the tail part of the signal. Here, it's much better. Situation is much better. In this particular time interval, you have only S2. In the overlapped symbol part, you only have the cyclic prefix, which is overlapping. And even if it overlaps part of the other signal, still we have a copy of it available in the other part of the signal. So having a cyclic prefix in front of the OFDM symbol helps reduce inter-symbol interference and help reduce the fading effects, the multipath fading effects. And as I said before, the length of the cyclic prefix will depend on the cell size. Large cells will have a longer cyclic prefix, and smaller cells will have a smaller cyclic prefix, because the channel delay spread is short in case of femto cells and very big in case of macro cells. Okay. Now, there are some challenges too. So OFDM, we have talked about all the benefits so far, but there are challenges too. As we said before, there are so many subcarriers in the OFDM signal, and there must be very tight synchronization between the transmitter and receiver. As we said before, a very strict subcarrier spacing has to be maintained. Only then we can maintain orthogonality between the subcarriers so that they do not interfere with each other. Loss of synchronization will cause inter-carrier interference. Now imagine if the synchronization is lost. So then the subcarriers will interfere with each other. Now the second challenge is the phase noise. Of course, the phase noise is there. We have to deal with it. So it can impair modulation quality or error vector magnitude, EVM. So we have to know how much of impairment we can tolerate for a particular receiver architecture. And the last one, it gives rise to large peak to average power ratio. Now this happens because we are adding so many subcarriers. We are modulating one subcarrier with data, another subcarrier with data, and so on. And I said there could be hundreds or thousands of subcarriers for a particular technology. So doing all this addition or summing up of subcarriers gives rise to peak to average power ratio, very high PAPR. Now this has an impact on the power amplifier. That means you need more complex circuits and you need highly linear power amplifiers because of this ratio. So we have to deal with it. You have to clip the signal so that the peak power is trimmed down. So this is another challenge to be tackled when designing OFDM receivers. Well, a typical OFDM transmitter will look something like this. You have the data coming in, serial data coming in at the left side. Then you have a serial to parallel converter, because remember we need to have multiple parallel data streams based on the number of subcarriers. Then we have QAM modulator for each of them, which gives us an output of I and Q frequencies, the subcarriers here. So these are actual subcarrier frequencies. And now what we do here, we use a DSP function called IFFT, inverse fast Fourier transform. What we do with this, we take the time samples of each of these I and Q frequency signals and get a time domain signal output. We sample the frequency subcarriers and get a time domain signal output. Then the time domain signal output we convert serially, and finally we do a QAM modulation at the carrier frequency FC, and then we get the RF out. Now you might wonder, why are we using IFFT here, inverse fast Fourier transform? So you remember, like, if we didn't have IFFT, what we have to do? We have so many different subcarriers, you know. We will have to modulate all of them, right? Giving rise to a very complex circuit, and then transmit all of them together over a very wide band. Then we lose all the benefits of OFDM, because we are just transmitting subcarriers directly into the air. And we will lose the real benefits of OFDM if we do that. So instead, we make by doing inverse fast Fourier transform, we make a single composite signal, which is the OFDM symbol, which is the time domain version of all the frequencies here, subcarriers, which are hundreds of subcarriers or thousands of carriers. And finally make a composite signal and modulate that composite signal, which is a time domain signal, into the carrier frequency, FC, which is the actual carrier frequency transmitted into the air, which is RF out here. Okay, so at the receiver, we do the reverse process, because the received signal is the OFDM symbols we get, and then we have a serial to parallel converter, parallel data streams. But all these subcarriers are in time domain. Remember, we did a time domain conversion in the previous. These are time snapshots of all the frequencies. We have to do a reverse process here, fast Fourier transform. This is again another DSP function we have to do here, a fast Fourier, which converts from time domain to frequency domain. And then here we get the original subcarriers. Finally, here we just have to decode the signal. What we are decoding actually, as we remember from QAM, we need to decode the amplitude and phase combinations. That is the only information we need. For each and I and Q, what is the amplitude of each component and what is the phase? Once we know that, we decode our data out of it and then convert from parallel to serial, and finally we get the original data out here. So transmitter involves inverse fast Fourier transform to make a composite OFDM symbol, which is a time domain signal. We transmit that, modulate with the carrier frequency, transmit into the air, and at the receiver we do the reverse process, convert from the time domain samples to a frequency domain, from where we finally retrieve our data using QAM demodulation techniques. Well, Just taking a real world example here. Now, wireless LAN example. So these are the specifications for this standard 802.11 AG. Modulation technique is used as OFDM. Carrier frequency is 2.45 gigahertz or 5.8 gigahertz. There are 52 subcarriers here. There we use 48 for data and 4 are pilot carriers. Subcarrier numbering is like this: -26. There is a center carrier here, 0 and 26. And 0th subcarrier is not used. Spacing is between each subcarrier is 312.5 kilohertz. Carrier symbol rate is 250k symbols per second. Symbol duration is 4 microseconds. The guard interval or cyclic prefix of 0.8 microseconds. And these are the pilot subcarriers. Subcarrier modulation could be either BPSK, QPSK, 16QAM or 64QAM. Now, why we have these multiple modulations mentioned here? This is to support multiple data rates. You know, any of these wireless and technology, they can support from a low data rate to higher data rate. So as you move to high data rates, we use different modulation techniques. So channel bandwidth, this is channel bandwidth of the complete channel of all the subcarriers added together. That is 16.25 megahertz. It's a wideband signal. And channel to channel spacing, 20 megahertz to 25 megahertz. Okay. So let's look at a little more about this. So for this particular standard, the EVM, the error vector magnitude, they mention it should not exceed -27 dB. That is the limit. We have to keep it below. So typically a -40 dB of EVM is tolerable in this case. Typical peak to average power ratio has to be 17 dB. Now here you see for different data rates in megabits per second, from 6, 9, 12 and so on up to 54, how the modulation technique changes from BPSK to QPSK to 16QAM and 64QAM. And now there is another code rate mentioned here, forward error correction, FEC code rate, K/N. So what is this K/N? Or 1/2, 3/4 and so on. So what this means, for every 1 bit of actual data, we transmit 2 bits. 1 additional bit is for error correction. For 3 bits of data, actual information, we transmit 4 bits, total of 4 bits of data, where 1 additional bit is for forward error correction and so on. So K/N, K is the actual number of bits which carry information transmitted, and N is the total number of bits transmitted, where N minus K will be the number of error bits. So these error bits are used for forward error correction. Okay, the final column here represents the sensitivity requirement in dBm. How sensitive should be the receiver for each megabits per second? So if you notice, like as we increase our data rates, our sensitivity numbers are lower in negative, but actually higher. You know, -65 is a higher dBm level actually in negative terms. So why is that so? You need a stronger signal to support higher data bit, higher megabits per second. Like for 54 megabits per second, you need to have at least -65 dBm signal. For 6 megabits per second, you need only -82 dBm, right? So does it make sense? This is coming from the standard. So every standard will have this type of specification if you look at the specification document. Now let's pause for a while. So which one is correct? OFDM allows overlap of subcarriers causing significant adjacent channel interference. Cyclic prefix mitigates ISI. Tight synchronization is essential to avoid ICI. High PAPR can saturate amplifiers in OFDM receiver. Okay, good. Some of you are answering. Well, number 2 is correct. Number 1 is not right because the overlap does not cause any interference. Tight synchronization is essential. Yeah, number 3 is right. High PAPR can saturate amplifiers. Yes, it can. So number 1 is false actually. So number 1 is not right because you know OFDM allows overlap of subcarriers, but it does not cause significant interference. This is a negative statement here. Okay. This is a calculation of the sample data rate in case of the 802.11 standard. So let's take an example here. For we use, let's say we use 64 QAM. That means 2 exponent 6 states or 6 bits we are using. Code rate we are using 3/4, and the symbol rate as per the standard is 250k symbols per second. Number of data subcarriers is 48. We just do this multiplication to arrive at the data rate. So symbol rate multiplied with subcarriers, number of subcarriers, multiplied with bits per symbol, and multiplied with code rate. So remember, the code rate is important here too, because for every 3 bits of actual data, we are actually transmitting 4 bits, 1 bit extra here. So multiplying all this, we arrive at this 54 megabits per second. So there is always some overhead inbuilt in the bandwidth. When we say 54 megabits per second, it includes the error bits too. Okay, let's move on to the next one. Now, okay, let's look at a little more detail in the receiver architecture. So we want to decide that which receiver architecture is best for wireless LAN. Now, this case one, we are taking a super heterodyne receiver. Now, let's design a super heterodyne receiver for wireless LAN. So, as per the principles of super heterodyne receiver, we have a passband here for the frequency range of the wireless LAN. We have an image reject here, which rejects any frequencies outside this particular band. There's a low noise amplifier too. Then we have a local oscillator, which is a RF phase lock loop, which is at a difference of 1280 megahertz. We chose a IF of 1280 megahertz. So difference between 4920 and 3640, or 5805 and 4525, is 1280 megahertz. We get IF frequency out. This is SAW filter, surface acoustic wave filter, which is a very expensive one. And we feed this to a programmable gain amplifier. This is an amplifier. Finally, we get into the I and Q mixers, which have their own PLL here at 1280 megahertz. Now here, we are just mixing with the 1280 megahertz to retrieve the signal here. The two components of the signal, I and Q. Low pass filter goes on to the PGAs again, and then you have the analog to digital converter, and then we have a digital filter. Finally, we get 6 to 54 megabits per second of I and Q. So this is, the same. All those benefits will be there. You have high gain and selectivity and all that stuff. It's a super heterodyne receiver, right? But what are the pros and cons of this, doing like this? Pros, we have high gain with improved stability. There are no DC offsets. DC means there is no DC component in the output signal because it's a super heterodyne receiver. We have better IQ matching at IF. What is this IQ matching at IF? Here, if you see the picture again, this split into I and Q we do at IF stage, which is at a lower frequency. We are not doing split here at the upfront. Here, we still maintain the composite signal, and it's only at the IF stage we split them into I and Q. So, which is much more easier to implement. Now, what are the cons? It's expensive and large. We have so many discrete components, which adds to the cost of the receiver, and you need multiple IF filters for multi-mode applications. Now, what are multi-mode applications? Today's handsets and cell phones, they don't have just Wi-Fi. They also have 3G and 4G interfaces. So for each of these bands, you will need multiple IF filters, and IF filters are expensive to implement in such a small handset. So that is a downside of this. It will add to the cost. For multi-mode applications, you need more IF filters, more discrete components that will add to the expense and add to the size of the receiver. So let's look at another implementation, a low IF receiver. Now what we do, we reduce the IF frequencies, the intermediate frequency. We reduce it down to 10 megahertz. Instead of 1280 megahertz, we reduce it down to 10 megahertz. Hoping that this will reduce the cost of our filters and multi-mode application and all that stuff. So here but here what we do, to do that, we split into I and Q at the front end. We split them into I and Q at the front end. We have these two components, I and Q, at the lower frequency 10 megahertz, and finally we filter them out, convert to analog to digital, and finally we have 6 to 54 megabits per second. Now it is still IF, although IF is reduced and we are splitting at the front end itself, but it's still IF, and there will be some pros and cons here too. So pros are no need for IF SAW filters because the frequency is much low. IF SAW filters are needed at higher frequencies. So no need of IF SAW filter and a PLL for IF. That will reduce the cost definitely. No DC offsets because it's a super heterodyne. Better integration. Narrowband applications. So it does find use in narrowband applications such as Bluetooth and GSM. All IF super heterodyne receivers, one thing is it's very good for narrowband applications because with IF you can improve selectivity. So it does find, the low IF receiver does find use in Bluetooth and GSM applications. But what are the cons? We have a quad IQ RF down converter, which is difficult to implement. We are splitting I and Q at the front end itself. We need to split it here itself. So that is expensive to implement. We are having a RF PLL which is 4 gigahertz here. So much higher frequencies. which will add to the cost and complexity and the difficulty of implementing. So many discrete external components. You have additional second low IF quad IQ mixer and not ideal for broadband applications such as wireless LAN. So wireless LAN is a broadband application. With IF it's a narrowband. IF is more suitable for narrowband applications. So that's why the low IF does have applications for narrowband applications like Bluetooth and GSM, but it's not good for broadband applications such as wireless LAN or LTE. So finally we come to the final case 3, which is direct conversion receiver. This does find applications in broadband applications. So here again, as we have seen before in a previous architecture, we do need to split I and Q at the front end. That is of course a challenge, but we have to do it. There is no other way. And then we split, we get the I and Q signal just at the output of here in the front end, baseband signal. The baseband signal directly goes to ADC converters, and then we have a digital filter here, and the signal is ready to be processed here. So what are the pros and cons of direct conversion receivers? Lowest cost, because you have very few elements. Good performance and low power on wireless LAN. No need for expensive IF SAW and IF PLL or image filtering. What are the cons? Quad IQ RF down converter, difficult to implement, but now CMOS implementations are available now. With the latest advances in CMOS fabrication techniques, there are quad IQ RF down converters which are implemented in CMOS. So of course, but you will have DC offset problems. How does DC offset problems come in? You know, what happens here in this case, if you look at the diagram again, now this local oscillator here, which is again 4.9 gigahertz to 5.8 gigahertz, it can leak into the antenna actually. You know, the oscillator frequency leaks into its own antenna and then enters the mixer and then mixes with itself. That causes a DC offset problem. It gives rise to a DC component. What is the downside of DC component here? The DC component can change the operating point of the amplifiers. No, the operating point is set at certain middle point here, which keeps the signal variations within the linear region of the amplifier. But if you have a DC component, it will shift the operating point of the amplifier, causing the signal to overshoot into the non-linear region of the amplifier, and that gives rise to distortion. So we have to deal with this DC offset in this case. How do we do that? One option is that we use not the same frequency but twice the local oscillator required to avoid coupling, so that it doesn't couple with the antenna. We use a twice or half or maybe 3 times or 4 times the local oscillator frequency, so that it doesn't couple with the antenna. Another downside is this is because of the CMOS implementation. In CMOS implementation, it's very prone to the flicker noise. Now, flicker noise is a low frequency noise. You know, it happens at lower frequency range, so that we have to deal with. But you know, in case of OFDM, it is still we have some resistance because our frequency band is like 20 megahertz, 25 megahertz. Even if the lower subcarriers are affected because of flicker noise, still we can have redundant information in the higher frequencies. So OFDM, because of wideband, because of so many subcarriers, gives us a little advantage. We can overcome this flicker noise problem also, which is inherent in CMOS implementations. Well, this is the final topic here, but very important one, at least we should be aware of it. Software defined radio. Some of you, okay, there is a question here. What is a phase lock loop? Now, of course, we are not covering this phase lock loop here because that is not part of the scope of this webinar. Of course, you can find some references online for this. If you are electrical engineer, you always study about this phase lock loop PLL in your college course. So what happens here? The phase lock loop basically it's used to maintain a stable frequency of the oscillator. So it's a feedback mechanism. You know, any oscillator will generate some frequency, but how do we ensure that the frequency remains stable at, let's say, 4 gigahertz or 2 gigahertz or whatever frequency we are generating inside the receiver? So phase lock loop is a feedback loop from the output to the input of the oscillator. So we constantly using some implementation, hardware implementation. We constantly monitor the output frequency, and if there is any variation, we compare with the input. And if there is variation, we will adjust the oscillator to maintain at a stable point, to maintain the frequency at a stable point of whatever frequency it's going to generate inside the receiver. So PLL is used to stabilize the frequency of the oscillator. So phase lock loops provide you a very stable local oscillator. So remember, previously we said, like in any wireless receiver, stability is very important. So PLLs help us achieve that stability in the frequency that is generated inside. Same holds for transmitters also. transmitters will have PLLs to stabilize the RF oscillator frequency which is transmitted, so that you can maintain your carrier frequency at a fixed point. It doesn't change with time. It doesn't drift with voltage. It doesn't drift with temperature. If there is a drift, it's fixed. It's automatically taken care of by providing a feedback loop. So that is what I can cover in this, but you can definitely refer some good. There will be very good resources available online or in some textbooks for PLLs. Okay, software-defined radio. Now we have seen with the QAM and all these things that we always need some processing in the baseband signal, some processing of the baseband signal. That processing means that we need some software, we need some algorithms, some programs we can use to process the baseband signal. So that is where the motivation comes from this software-defined radio. Then why don't we make an attempt to implement all receiver, the complete receiver in software? That is the ultimate idea. So radio functions implemented in software, we use digital filters. We have algorithms for finite impulse response or infinite impulse response or adaptive filters. Our goal is to implement notch filters or even equalizers. We reduce noise or even AGC, automatic gain control, even modulation, demodulation techniques, or even local oscillator. All these different functions of the radio can be implemented in software, and that gives rise to the term of software-defined radio. Now, what is the hardware? The software runs on some hardware anyway, right? Software is not standalone. So the hardware design is consisting of a combination of DSPs, that is digital signal processors, which implement DSP algorithms. You could have application-specific ICs, integrated circuits, or you could have FPGAs, field programmable gate arrays. So in conventional designs of radio, this is very prevalent. The implementation of radio by using combination of DSPs, ASICs, and FPGAs, and running some software algorithms to implement all those functions. Another attribute of SDR is the reconfiguration. If it is software, you can download the software to change the function of a software-defined radio. Okay, there is a question here. Which software, for example, can be used to design such functions? Okay, let's first move a little further, then we'll try to answer this question. Okay, that will depend on your requirement, what you want to do, what type of SDR you want to do. So what are the download mechanisms that could be used in SDR? It could be static. That means you have your receiver and you just insert a smart card in the receiver, and that configures your software-defined radio. It could be pseudo-static. That means over-the-air reconfiguration. What that means, that your wireless receiver already has uplink and downlink connection with your base station, and over the air you could reconfigure. Like let's say that you are switching from CDMA to LTE, that you could reconfigure your receiver to do the LTE function instead of CDMA, or vice versa. Or you could add a new feature to your receiver over the air. Dynamic is over the air reconfiguration during a call. What that means, that now you are making a call, you are making a video call on your receiver, but you also want to add a little more. You want to add this web browsing, for example, or something else. You want to do it at the same time. While you are on a video call with one person, you are doing web browsing also, let's say. So you want to reconfigure your receiver to receive that particular bandwidth. It could be a different bandwidth than what you are doing in a call, using in a call. So dynamic download mechanism enables reconfiguration during a call. Okay, so now let's be a little more, let's see that how do we classify different types of, this actually slide shows the progression in the advancement of SDR, software-defined radio. At level 0, you have a conventional implementation in hardware. This is the conventional, like you have your conventional AM or FM radio in your car. That is a level 0. So we call it level 0 SDR, no software actually. Then level 1 is software controlled radio, where your RF radio functions are in hardware, but you can control them using software. You have some sort of a user interface, a touchpad or something, which you can use to configure your hardware functions. Level 2 is the software-defined radio, where your modulation and baseband processing is in software, but RF functions are still in hardware. Your front-end RF functions closer to the antenna are still in hardware. Then the next level of progression is the ideal software radio, ISR. That means everything from antenna onwards is in software. Ultimate software radio, where you have dynamic transition between communication protocols. So let's see some of the illustrations here. Now this is the conventional. We have seen this slide before also. Everything is in hardware, so this is level 0. Level 1 is the software controlled radio, where you have all these functions still in hardware, but you have a man-machine interface or a user interface, where you have software which can control the configuration of all these hardware elements. You could change the bandwidth, for example, RF filter, you could change the filter characteristics. In the RF amplifier, you could change the gain of the amplifier. Local oscillator, you could tune it using a man-machine interface. IF amplifier and discriminator and so on. So software controlled radio. Well, in this case, this is a software defined radio, level 2, where as you see, your RF functions, local oscillator still in hardware, but once you retrieve your baseband signal and you have, once you have this, the ADC here, you need to demodulate or discriminate the signal, then you use software. You use software for all baseband processing and even demodulation discrimination. So this is all in software. Here you will have DSPs, FPGAs, ASICs, combination of these 3 items, and implement the software defined radio functionality. Well, next level is the ideal software radio. You know, here everything is software. At the front end, you just have the antenna, and then you have an ADC. Once you digitize the received signal, then you do everything in software. Digital IF processing, discriminator, demodulator, and baseband processing, and so on. Of course, you have a man-machine interface here too, to control all the different functions. And finally, you get the signal output. Well, these, the level 3 and onwards, they are still in the future. You know, there are attempts by various vendors to implement all these functions in software. It's a very hot research area too. But the benefits are many if you do this. What you can do with the ultimate software radio, you can switch between technologies, CDMA, GSM, LT, Wi-Fi, or even any feature modulation technique that comes in. Let's say, like somebody had a question before, like now we have OFDM, maybe 5 years from now we'll not have OFDM. So what will be the change? The change will be most likely in the software, because you have new algorithms coming in, new techniques coming in. Those new algorithms can be implemented in software. So here they are more, now coming back, okay, there is a question here. Is there any controller which separates the control and the forwarding plan? Well, that will depend on your implementation. There is no specifics here. These are only very high level architecture diagrams. That will depend on how you implement your software defined radio. There could be multiple ways of implementing it, right? How inside the box you do the things. Are you separating the control and the forwarding plan? Well, yeah, definitely there will be a control path and there will be a forwarding plan, but it mostly depends on how you implement inside the box. So for this, if you want to really see, you have to really go online and do some research. How some of the vendors are trying to implement this, the ultimate software radio or software defined radio, trying to put all the functions in software, right? There are different platforms available, and it depends on which vendor does what. They are mostly proprietary stuff. Well, so benefits. What are the benefits of SDR? Enhanced upgradability. It's very easy to upgrade now because you are just upgrading the software in most cases. Of course, sometimes you will see, okay, I have new software, now I need to upgrade the hardware too. But what will be the upgrade in hardware? Hardware, you will need more capacity of DSP or more capacity on FPGA or the ASICs. But the most value addition will be in the form of software. Customizability. You can customize the same hardware for different applications by just software. Reconfigure. It's easy to reconfigure by over the air or even offline reconfiguration. So why we need to reconfigure? What is the benefit of reconfiguration? We can implement new standards of protocols, like we have a new version of LTE, and now we have LTE Advanced or Release 11 or Release 12 coming in. It's very easy to implement those new standards of protocols when you have a software-defined radio. Okay. Is it defined by ITU or is it under control of the open flow specification? Well, there's no, SDR is more in the open flow specification. ITU just defines the telecom protocols and standards, which protocols to be used where. It's up to you how you implement this. You want to use open flow specification or you want to use your own proprietary method. So it will be how the industry takes it, basically, how industry goes about it. So its technology is not mature, it's not mature to that
level, but once it matures, there will definitely be some standards coming in for this too. And this time it's more vendor specific, and there are some open flow specifications too. If you research online, there are some open flow specifications too available which you can use. So you can implement new standards or protocols. You can bypass failed hardware. You could have redundant hardware inside the box, and one part fails, you can activate the other one remotely. Reconfigure access network due to change traffic pattern. So you could redeploy your resources on the base station for peak traffic or for low traffic. Like at midnight in a specific location, traffic is very low. The same resources could be shared by something else for something else actually. So you could reduce visits to cell site because of the software part in this. Many things can be done remotely. So the visits to cell site are reduced. More cost savings. This radar application, you could implement new pulse schemes which are easily implemented. Instead of designing everything in hardware, you can just change the algorithm in software to implement new pulse scheme. RFID readers, if they are based on SDR, they can support multiple protocols. So any modulation type can be implemented, not just QAM. You can implement AM and FM also. So definitely SDR gives us more flexibility, and that is a goal. Well, yeah, there is a question here. Definitely, we engineers need to review our programming languages and algorithms. Yeah, definitely true. So these days, if you are an electrical engineer or a telecom engineer, that means you have to know software too, very specific software. How do you write DSP algorithms? How do you develop programs for DSP, for example, right? So knowing C and some proprietary language may be good enough for that, because you are not developing high-level applications here. You are only writing programs for DSPs, right? And select one model, say Verilog or something else, and you can specialize on that. But of course, that will pay you only if you are working for a company that is developing, that's a vendor of these equipment actually, right? And they have a need for a DSP engineer. A lot of software is involved here. Well, what are the challenges? So SDR is not free of challenges. They have challenges too. Security, as is true for any software which is delivered over the air. Challenge is to implement a secure software download. You don't want your wireless receiver to be hacked by somebody, right? Like somebody remotely hacking into your radio functions and disabling it or using it for some different purposes. So secure software download is definitely a challenge which has to be taken care of. Processing power. Now, as we said before, like new algorithms or new protocols can outpace processing power. So 5 years from now, you have a new LTE version of the LTE standard. That means the current hardware, the 5 years old hardware, may not be enough. You need more capacity, more bang for the buck. So despite these two challenges, SDR is going to stay. Right? This is the future. And many vendors already have plans to put more and more software-defined radio in their base stations and in their handsets. Okay, so this is a list of some papers and books, and now finally we have the final slide. Information to claim 1 PDS credit and certificate of completion. This is the link you can use to complete your requirements to answer the problem statement from this webinar to get your certificate of completion. And down here is my contact information. You can visit our website to learn more about our services. And before we end the webinar, let me ask if there is any question you can answer here. Please ask any questions. Okay, so even offline you can send me email, ask me any questions and any other things you need from me from today's webinar. And so thank you very much for attending this webinar, and I'm going to close this conference and wait for a window to pop up on your screen that will take you to the link, the webinar forum page, where you can complete your requirements. Thank you very much.